Hello everyone, welcome to the lecture on 3D computer vision. And today we are going to talk about camera models and calibration. Hopefully, by the end of today's lecture, you will be able to describe the camera projection with the pinhole camera model, and you'll be able to identify the camera center, principal planes, principal point, and principal axis from the projection matrix. We'll then look at how to use the projection matrix to get the forward and backward projection of a point, and we'll explain the properties of an affine camera. Finally, we'll do calibration to find the intrinsics and extrinsics values of a projective camera. Of course, I didn't invent any of today's material. I took most of the contents of today's lecture from the textbook written by Richard Hartley and Andrew Zisserman, Multiple View Geometry in Computer Vision, in particular Chapter 6. I also took some of the materials from Chapter 3 from the textbook written by Ma Yi, An Invitation to 3D Vision, and I took the calibration method from a paper written by Zhang Zhenyou, a flexible new technique for camera calibration, which was published at TPAMI in the year 2000. I strongly encourage every one of you to take a look at these materials after today's lecture. In the introductory part, we look at the basic definition of a camera. It's essentially a very simple device that maps any geometric entities in the 3D world onto a 2D image plane. And we look at the 2D projective space denoted by P2. This is essentially a projective plane where we define geometric entities such as a point, a line, as well as the conic. And we also define the hierarchy of transformation that maps the geometric entities from a P2 space to the same space. And furthermore, we also look at the geometric entities in the 3D projective space denoted by P3. And we also look at the transformation, the hierarchy of transformation that maps these entities from the P3 space to the same space. And this geometric entities includes a point, the line, plane, as well as the quadric. In today's lecture, we'll look at the projection matrix that maps the 3D geometric entity in the 3D projective space onto the projective 2D space. We'll look at a specific type of camera model, which we call the camera model with a central projection in this particular lecture. And what it means is that all light rays that is being projected onto an image plane, they will converge at a single center of projection. And generally, camera models with a central projection falls into two major classes. The first type is a camera with a finite center. What this means is that this particular point here, if I denote it by C, I express this particular coordinate in the R3 space. That means that it's in the 3D space. This particular coordinate with respect to a world frame, it will have a finite value. The second class of the camera models with a central projection would be those with a center at infinity. And if I denote this particular camera center, it will lie on the plane at infinity. We'll find out more detail about these two classes of camera models, those with finite center and those with center at infinity. In particular, we'll look at two camera models. The first type, which we call the projective camera. This is a representative camera model with finite center. And the second type that we will see would be the affine camera, where the center of the projection lies at the plane at infinity. So a projective camera can be defined using the very basic pinhole camera model, which is what we are going to look at now. Let us first define a Euclidean coordinate, which we can see this illustration where the y-axis is here and there's a x-axis and there's a z-axis that's pointing out. So where the center of projection is being defined at the origin of this particular Euclidean coordinate system, which we denote by C over here. Now, let's consider the image plane, which is a plane that is parallel to the xy plane of the Euclidean system that we have defined. There is a certain distance in the z direction that is spaced out between the xy plane of the Euclidean coordinate system that we have defined earlier on and this particular image plane. And we define this particular distance as f, which you will see that this is actually the focal length later on. And we call this particular plane either the image plane or the focal plane. And now, having defined this, if we were to look at the side view from this particular point of view, we can represent this projection system onto where a point X in the 3D world, it actually joins up the camera center via a light ray, where the intersection of this particular point, which we call small x over here, it's actually the image projection of this particular 3D point onto the image plane following a camera model with a central projection. So now, by the virtue of similar triangle, we can see that there's two triangles over here. One which is the smaller one, which is here, and the other one which is the bigger triangle, which is given by this guy over here. We can see that the base distance of the smaller triangle is essentially given by f, which we have defined earlier on, and the base distance of the largest triangle, let's denote it by z, and the height of the larger triangle is also given by y, which is essentially the inhomogeneous coordinate of the 3D point that is being projected onto the image that we have seen earlier on. By the virtue of the similar triangle, the height of the smaller triangle is naturally given by the product of f over z, which is the ratio of the base length multiplied by the height of the bigger triangle. Now, we can formally express the 3D to 2D projection as the coordinate form, where given a 3D coordinate denoted by x, y, z, it's actually mapped onto the 2D space of f, y, where the y coordinate is being mapped onto f, y over z. We can follow the same concept of similar triangle to derive the x coordinate of the projection of this 3D point on the image coordinate. We will find that this is given by fx over z. Since we are projecting it onto a 2D space, we can ignore the third coordinate, which is essentially the distance of this plane from the xy plane of the Euclidean coordinate f. Now, this can be seen that it's a definition of a 3D projection onto a 2D space. We'll further define some terminologies in the basic pinhole camera model. So we have looked at the camera center, otherwise can be known as the optical center. This is essentially the point where all the light rays that is being projected onto the camera will meet. And there's another definition which we call the principal axis, and essentially this is the z-axis of the Euclidean coordinates that we have defined. So this particular principal axis is perpendicular to the image plane, and we will also define what is known as the principal point. So principal point is essentially the point of intersection between the principal axis and the image plane. And finally, we'll define what is known as the principal plane. So the principal plane is essentially the plane that lies on the xy plane. So this guy here is the principal plane, and this is the plane that lies on the xy plane of the Euclidean coordinate. Now, we can see that the mapping from the 3D coordinate onto the 2D image plane, it can be expressed as a linear mapping if we were to write it in terms of homogeneous coordinates. Previously, we wrote that this is the 3D point, this is the coordinate of the 3D point, which essentially lies at x, y, z, and if we were to write it into homogeneous coordinate, we will add a 1 at the end. And then we saw that by the virtue of a similar triangle, the x coordinate on the image plane is denoted by fx over z, and the y coordinate of the image plane is denoted by fy over z. If we were to express these inhomogeneous coordinates into a homogeneous frame, we can bring the denominator, the common denominator, which is z, and put it into the third coordinate in the homogeneous coordinate frame. And now, essentially, this becomes fx, fy, and z in the homogeneous representation. We can see that we can factorize these terms over here, the homogeneous coordinate fx, fy, and z, into a 3x4 matrix multiplied by the 4x1 vector, which represents the 3D point. So this 3x4 matrix can be further simplified because it's actually a diagonal matrix which consists of f, the focal length, as well as 1. We can further factorize this into a 3x3 matrix which consists of a diagonal entries of f. So this matrix here is essentially equals to f0, 0, 0, f0, and 0, 0, 1. And then multiply by an identity matrix 1, 1, 1, followed by all zeros here. So this guy here is 3x4, and this guy here is a 3x3 matrix. So essentially, if you multiply these two matrices together, this is the matrix that you will end up with. And now, with this 3 by 4 matrix, and if we multiply it to the 3D point, what we will recover here is essentially the 2D projection fx, fy, and z over here. Let's further denote P equals to this matrix that we have factorized earlier on, and it simply represents the diagonal matrix multiplied by the identity 3 by 4 matrix that we have seen earlier on. And we will denote small x as the 2D projection on the image, and the big X as the 3D point that we have seen. In short, we can simplify this equation into this form where x is equals to P multiplied by x. The small x here is actually a 3 by 1 homogeneous coordinate. P here is a 3 by 4 matrix, and x here is a 4 by 1 homogeneous coordinate. And we'll give this P matrix, which is a 3 by 4 homogeneous coordinate matrix, a name, and it will be called the camera projection matrix. We have seen earlier on that the origin of the 2D coordinate frame is being defined at the principal point of the image, which is often the center of the image. But in practice, the origin of the coordinates in the real image plane might be defined anywhere, need not necessarily coincide with the principal point of the coordinate system, and we can in fact define it anywhere. Say for example, let's define the reference frame of the image reference frame as small x and y that is being assigned to one corner of the image, which essentially means that the principal point is now px and py with respect to the image reference frame. And what we need to do here is that we need to compensate for this px and py with respect to the reference frame of the image. So as a result, we can see that the projection from the 3D point, so this is the 3D point, the projection that we have seen earlier on from the 3D point to the 2D point, it's no longer just these two terms, fx over z and fy over z alone. Now we have to compensate for the translation of the coordinate frame by an amount of px and py in the respective direction. We can express this particular expression here, which is in the inner homogeneous coordinate frame, into a homogeneous coordinate, and we can see that this becomes a linear mapping. What I meant by linear mapping here is that it simply becomes a matrix multiplied by a 3 by 4 matrix multiplied by a 4 by 1 homogeneous coordinate. The two additional terms that we have seen that defines the principal point, it appears as a px and py over here. So if we were to evaluate the multiplication of this 3 by 4 matrix with the 4 by 1 vector over here, we will get the 2D coordinate frame, which is fx plus z, px, and fy plus z, py, and z here. So now let's further write this 3 by 4 matrix into a factorization of what we call the K matrix, but multiplied by a 3 by 4 identity matrix, where this particular K matrix here can be expressed as this 3 by 3 matrix over here. The diagonal consists of the focal length f and 1, and then the principal point will appear on the third column of the K matrix. So essentially, if we were to multiply K, this matrix over here, by 1 and 0, and this guy here is a 3 by 4 matrix, what we will get back would be the original matrix over here. So this is simply just a reorganization or a refactorization of the matrices. And now we'll also give this K matrix a name. We'll call it the camera calibration matrix. This particular K matrix is also otherwise commonly known as the camera intrinsics matrix. If you have noticed earlier on that this particular 3D point is actually expressed in the camera coordinate frame, which is this particular guy over here, that we have defined the location of the camera center, the principal axis, the principal point, as well as the principal plane. But in practice, any 3D point that is given to us might not always be expressed with respect to this camera frame. It could be expressed with respect to any arbitrary frame, which we call the world frame, where the camera frame would be at a certain rigid transformation away from the world frame. that is denoted by R and T. So C here is actually expressed with respect to this origin by a rigid transformation of R and T. That means that we should also consider the projection of the 3D point with respect to the world frame. Let's call this guy here x, y, and z, and 1, the homogeneous coordinate of this, which is expressed with respect to the world frame. So we'll call this capital X with respect to the world frame. The camera projection expression that we have derived earlier on, which is small x equals to k I 0 multiplied by big X. So in this case here, X is defined with respect to the camera frame. But let's say now X is defined with respect to the world frame. We would have to compensate for this rotation and translation in this projection equation. The aim here is actually to denote this particular point with respect to the camera frame instead. So this can be easily done. Let's denote the inhomogeneous coordinate of the camera center as C tilde. C tilde, essentially it simply means the x, y, and z coordinate of C with respect to this particular frame. That means that the camera coordinate is expressed in the world frame, and we will denote this by C tilde. So given any point, if we know this relation, and we also know that there is a rotation, that means that this particular frame, the orientation of this particular frame, the camera frame with respect to the world frame, it need not be aligned as shown in this figure here. It could be actually in any particular orientation. For example, this could be our camera frame that is not aligned, not perfectly aligned with the world frame. So there exists a certain rotation that relates the orientation of the camera frame in the world frame. Now, given a point x here, defined with respect to the world frame, what we want to do here is that we want to transform this particular point into the camera frame so that it will be consistent with this particular projection equation that we have defined earlier on with respect to the camera frame. And the relation, it will be simply given by a isometric transformation. This is a isometric or a metric transformation that we have seen in lecture 1, where the rotation is simply R, because the orientation of camera and the world frame is related by R. The translation amount here, T, is simply given by minus R of C. Applying this 4x4 matrix over here onto the 3D point that is expressed in the world frame, what we'll essentially get here is that we'll transform this point expressed with respect to the world frame into the camera frame, which we now denote as X cam. Now, put this particular X cam equation back into this projection equation, what we'll get here is that we'll get K I0 multiplied by R minus RC and 0, 1, and multiply by capital X, where this guy here is simply our X cam, which is consistent with what we have seen in the definition of the projection matrix earlier on, because this is a 0 here, which essentially means that after multiplication, the last row of this isometric transformation would be eliminated, and we can simply denote this as R minus RC X, which is our 3x4 matrix over here, and this guy here is our 3x3 camera intrinsics, and this is the 3D point that is expressed with respect to the world frame. So as we have also seen earlier on, rotation matrix is essentially over-parameterization of the Euler angle, which has 3 degrees of freedom: rho, pitch, and yaw. So if we were to look at this in the XYZ axis, so the yaw angle, a rotation matrix, is essentially obtained from first rotating around the z-axis, which we call the yaw, and we denote this by gamma over here. And then the second step that we do would be to rotate. After the rotation of yaw angle, we rotate with respect to the pitch angle along the y-axis, which is given by this rotation matrix over here. Finally, we apply the rho angle on the x-axis, along the x-axis. This is the final rotation matrix that represents the roll angle. And now, if we were to concatenate all the yaw, pitch, and roll together to get the final rotation matrix, we'll be able to represent any arbitrary rotation in the 3D space. So essentially, this is the rotation matrix. This guy here, this rotation matrix is the rotation matrix. We are interested in this isometric transformation, which means that is a general arbitrary rotation matrix that represents the orientation transformation from the world frame to the camera frame in any general case. These rotation matrices, it could be a 2 by 2 rotation matrix, which is in the 2D space. If we were talking about the R2 space, then this rotation matrix would be a 2 by 2 square matrix, or it could be also a 3 by 3 uh, a 3 by 3 square matrix when we are talking about rotations in the R3 space. So in this particular case, R2 space, then there will be only 1 degree of freedom, because essentially in the XY plane, there's only one rotation that is possible, that is the yaw angle. We can only have an in-plane rotation that is along the yaw angle. So this 2 by 2 matrix on the 2D space, it will have only 1 degree of freedom. But in the general 3D space, R3 space, we would have 3 degrees of freedom, which is what we have seen earlier on here, that is expressed, is parameterized by the roll, pitch, yaw angle, which we collectively call the Euler angle. So a rotation matrix, it's regardless of whether it's a 2 by 2 or a 3 by 3 rotation matrix, you will always have the following properties. The first property is that the determinant of R is going to be either +1 or -1, depending on how we define the coordinate frame. So in the right-hand coordinate frame, where we do this, x, y, and z is pointing in this direction, where when we move from x to y, our thumb is actually pointing towards the z direction. So if we use a right hand, our forefingers to do this sweeping action, our thumb is pointing towards the z-axis of the right hand. And in this case, we call it the right hand coordinate frame. And this is usually the coordinate frame that we use to express any Euclidean reference frames. And there's also another coordinate frame where if we were to do the same sweeping action with our left hand, then we will see that in this case here, we will end up having x here and then y here and sweeping this direction, where z now is going to be pointing in the same direction, but we will see that x and y swap direction. So if we were to be consistent, if we were to draw x in the same direction as the right hand coordinate frame and y in the same direction as the right hand coordinate frame as well, then we'll see that z points to the opposite direction, and we'll call this the left hand coordinate frame. So the difference between these two reference frame system is that the determinant of the rotation matrices that is expressed in the right hand coordinate system will always have a +1 determinant, and the determinant of the rotation matrix that is defined with the right hand coordinate frame is always going to have a -1. Since the rotation matrix is a octanormal matrix, what this means is that the transpose of the rotation matrix is going to be equal to the inverse of the rotation matrix. And hence, and also since it's an octanormal matrix, this means is that the axis of the rotation matrix has to be octagonal to each other. This means that the third column of the rotation matrix is equal to the cross product of the other two columns. In fact, any column of the rotation matrix is equal to the cross product of the other two columns that is in the rotation matrix. We can see that actually the rotation matrix over here, each column, it defines the xy axis. So the column 1 actually defines the x-axis, column 2 defines the y-axis, and the cross product of these two is going to give us the z-axis in the reference frame, and this will work for any combination. So if we will take z and x cross together, we will get the y-axis, and so on and so forth. So the rotation matrix, it actually defines the basis of the coordinate space. And what this also means is that since the cross product of any two of the columns is going to give the third column, simply because every one of this frame is actually orthogonal to each other. And this also means that the dot product of any two columns in the rotation matrix will always be 0, since they are perpendicular to each other. And the fact that it's an orthonormal matrix simply means that the norm of each column has to be equals to 1. So all these properties here simply points out that the rotation matrix, it defines the basis of the coordinate system. After we define x, the 3D points with respect to the coordinate frame. So if we recall that we have a 3D point x, and this 3D point is actually defined with respect to the world frame, where this is the origin, and then there is a camera frame over here that we define as FC, where the center of projection is actually given by C over here, and this particular frame relates to the world frame by R and T. If we were to express this particular coordinate expressed with respect to the world frame in the camera frame, we will get x cam over here that is related to the coordinate in the world frame by R and minus RC tilde. So this is the relation that we have seen earlier on. So we put it back to the general mapping of the pinhole camera. This is the relation that we have seen earlier on, where we can now factorize out the rotation matrix, which appear twice in the 3 by 4 matrix over here. This particular 3 by 4 matrix is actually equals to R and minus R tilde that we have seen earlier on. So this R here, since they are the same, it can be factorized out into rotation matrix that is in this particular form over here. So now we'll end up with the general mapping of a pinhole camera. This means that we will have a 3D point that is arbitrarily defined with respect to a world frame, any reference world frame, where the relation between the camera coordinate frame with respect to the world frame is by a rigid transformation of R and T. We can also write the projection matrix to take into account the rotation and translation of the world frame and the camera frame into this particular form over here, the P matrix. Now we can see that the P matrix still contains K, which is the intrinsic value. So this guy here, K is called the intrinsic value, and it also consists of the rotation and the translation, which is given by minus R and C, or the inhomogeneous coordinate of the camera center with respect to the world frame that we have seen earlier on. So this 3 by 4 matrix. So the intrinsics here is a 3 by 3 matrix, and this 3 by 4 matrix here is also what we call the extrinsics value, which consists of R and T. Altogether, the camera projection matrix has 9 degrees of freedom, where 3 of the degrees of freedom goes to K, because K, we have seen earlier on that K equals to F, and then Px, Py, and 1 over here. So there are altogether 3 DOF in the camera intrinsics, and then 3 other degrees of freedom goes to the rotation matrix. This is because we have seen earlier on that the parameterization, rotation matrix is actually an over parameterization of the roll, pitch, and yaw angle. So there's altogether only 3 degrees of freedom that can define any arbitrary orientation in the 3D space. Finally, there's another additional 3 degrees of freedom in the inhomogeneous coordinates of the camera center. And altogether, this adds up to be 9 degrees of freedom. I have said earlier on that the parameters contains in the camera matrix K over here, which is essentially F0 Px, 0F Py, and 001 over here. The parameters that's contained inside here is also called the internal camera parameters, because this really depends on the internally on the camera. We can also see this from when we are defining the basic pinhole camera. We first started off with the camera frame, and then we express everything in terms of the camera frame, we would already have obtained the K matrix in this particular form. So this is the 2D coordinate, and then we have a K multiplied by 0, 1, and X that is defined with X cam over here, that's defined with respect to the camera frame. Since K here is defined with respect to the local camera coordinate frame, we will also call K the internal parameters because it doesn't depend on the world frame, or otherwise the intrinsic values of the camera. There's another set of parameter which we call the extrinsics, as I have mentioned earlier on. So this set of parameters is just the R and C. So this is the camera center, and which relates the camera frame and the world frame. So this guy here, R and C, since it requires the world frame for definition, we will say that this is not internal to the camera. This is actually relying on external parameters, and or otherwise we'll call it the extrinsics of the camera. Is instead of writing this 3 by 4 matrix over here as what we have seen earlier on as this term over here, or rather R identity and the camera coordinate center over here. A more convenient way would be simply to collectively call this term here as T, the translation that relates the camera center with respect to the world frame. So the 3 by 4 matrix can be simply written as an isometric transformation which consists of the rotation matrix and the translation vector. So this rotation matrix over here is a 3 by 3 rotation matrix, and the translation vector is a 3 by 1 translation vector. Now, so far we have seen that the projection relation between a 3D world point onto a 2D image is based on the assumption that the image formation is based on a square pixel assumption. So what it means here is that on the image that we get, all the pixels are regular squarish point. Sometimes due to manufacturing error in the lens or the photo sensors that we have in cameras, these pixels, they might not appear to be perfect square. There might be some skew that occurs in the x direction. So in our camera model, we have to compensate for this non-square matrix or the skewness in the real cameras. So hence it's actually more accurate to have two additional things in our camera projection matrix. The first one would be different focal length, because we can see that there's a shift in the projection onto the matrix in the x direction, and hence there is a need to have different uh, focal length in order to define the similar triangle relation that we have seen earlier on in the beginning of the lecture. And another thing that is because we saw that the skew could happen in the x direction, and we would have to add another scaling factor in the x direction. So as a result, the camera intrinsic matrix would become fx, fy, where this replaces, we will have two different focal lengths in each respective direction that replace the same focal length in both direction, and as well as we will have a scaling factor as in the x direction over here. So the principal point remains the same. Now this becomes our new camera intrinsics metric. And as a summary, in general, we would have altogether now 11 degrees of freedom, where we have seen earlier the camera projection extrinsics over here, where R it's 3 degrees of freedom given by the Euler angles over here, and T over here is 3 degrees of freedom because we altogether have Tx, Ty, and Tz in the 3D space. Now K, the intrinsics, since we have two separate focal length in each one of the respective direction, which we denote by Fx and Fy, we'll have 2 degrees of freedom here. We have a skew factor, which we denote by S. So altogether, there's additional 3 degrees of freedom, plus 2 more for the principal point. So altogether, we have 5 degrees of freedom for the intrinsic value. And in total, 5 plus 3 plus 3, we will have altogether 11 degrees of freedom for our camera projection matrix P that is given by K multiplied by R and T. So essentially, a finite projective camera means that this is a camera with a central projection where all the light rays that are projecting onto the image have to converge at one single point of convergence. And this particular point of convergence, which we denote by C, it has to have a finite value with respect to a world frame illustrated here. And we've seen earlier on that the projection matrix is given by this particular equation over here, which consists of the intrinsics as well as the extrinsics of the camera. And we can now rewrite this projection matrix into another form, which is given by this particular equation over here, where we can denote M as a 3 by 3 matrix, and the remaining of the matrix would be a 3 by 4 matrix that consists of an identity matrix, which is 3 by 3, and the inverse of the M matrix of the 3 by 3 matrix that we have defined earlier on, multiplied by the last column of the original projection matrix. So what it means is that we are going to rewrite P as P1, P2, P3, and P4, where each of the P is a column in the original projection matrix. And we can see from this relation over here that if we were to multiply M inside, we will get this M and for the first 3 by 3 matrix, and the last column is P4, which essentially means that M here, which we have defined earlier on in this form of factorization, is equivalent to the first 3 columns of the original camera projection matrix. In other words, this is simply a refactorization of the original camera projection matrix that we have seen. We'll see later that for a finite projection camera, this M matrix over here, which essentially represents the first 3 by 3 entries of the camera projection matrix, it has to be non-singular in order for a finite camera center to exist. So of course, the first thing that we can define from a finite projection camera is the camera center, and we can see that this camera center has to lie in the null space of the camera projection matrix that is given by PC equals to 0. And what this simply means is that the projection of the camera center is going to be projected into an undefined point where this undefined point is going to be at 0, 0, 0. And we'll see a sketch of proof on why is it that the camera center has to be on the null space of the camera projection matrix. Let's first consider a line that consists the camera center C as well as any other point in the 3D space. And what this means is that I'm actually looking at a light ray that is a projection onto the camera center. So there could be many other light rays that converges to this, that meets at this single center of projection. And now I'm considering one light ray which contains the point A in the 3D space, and this actually joins up with the camera center C to form a line which we denote as X over here, and this is given by the span of the 2 points A and C, which I have seen in the past lecture. Under the projective mapping, where a 3D point is being projected onto a 2D image point, this is developed from the basic pinhole camera model that we have seen earlier on. We can make use of this projection to project this line, any point on this line, which we denote by X. It's being projected onto the image via the camera projection matrix that we have defined earlier on. And now let's substitute this X lambda by this the span of A and C into this equation. We'll see that the projected points can be decomposed into two terms over here, where the first term is simply the projection of A, this 3D point, onto the image. And the second term here, it's the projection of the camera center to the image point. And we know that A could be any point on this line. And we know that any point on the light ray, it has to be projected onto the image plane as P of A, which is defined by this mapping over here. So what this simply means is that the second term here that is given by the projection of the camera center, it has to be in the null space. It has to be equals to 0 in order for this relation x equals to PA to hold true. Hence, we conclude that the camera center must be in the null space of the camera projection matrix. So let's write the camera projection matrix into 4 columns that we have seen earlier on, P1, P2, P3, as well as P4 that we have seen. We can see that the first 3 columns of this projection matrix actually defines the vanishing point of the world coordinate x, y, and z axis respectively. What this means is that the point that is being given by the z-axis, for example, the infinite point, this is going to intersect the plane at infinity at an infinite point over here, which is actually given by 0, 0, 1, 0 transpose, because this last term here has to be equals to 0 for it to be an infinite point, and the first 3 terms simply says that this is in the direction of the z-axis, so it has to be 0, 0, 1. So this particular point here, when it projects back to the camera, it actually lies on this point, which is P3, which we can see by looking at the projection. So if I were to take this P1, P2, P3, which is essentially the camera matrix P, multiplied by this point 0, 0, 1, 0, we can see that the first column here multiplied by 0, it will turn out to be 0. Similarly, P2 multiplied by 0, it will turn out to be 0, and only P3 would remain. So what this means is that the projection, the ideal point that is from the z-axis, it would have to project to a vanishing point of P3 on the image. So this is similarly for the x-axis here, for example. So in the x-axis, we can see that this guy over here, it intersects the plane at infinity, at a point of 1, 0, 0, 0 transpose. This has to be 0 for it to be an ideal point, and the first 3 entries is simply the direction of x. So we can see that if we were to multiply this guy over here with P1, P2, P3, and P4, which is the camera projection matrix, multiplied by 1, 0, 0, 0, and only the first column remains, which is P1. So hence, P1 here would be the vanishing point of the ideal point that is in the direction of the x-axis. And what's interesting here is that the last column of the camera projection matrix is actually the projection of the origin of the world coordinate frame, and we can easily verify this by looking at this, since the origin of the world coordinate frame has to be at 0, 0, 0, 1, this particular point over here. So if we were to pre-multiply this by the camera projection matrix 0, 0, 0, 1, we can see that only the last term over here, P4, remains. Hence, P4 has to be the projection of the origin of a world frame that is being projected onto the camera image. Now let's look at the row vectors of the camera projection matrix, and we'll see that the row vectors actually corresponds to a particular world plane in the 3D coordinate frame. So let's denote P1 transpose, P2 transpose, and P3 transpose as the respective row. So Pi transpose here is actually a 4 by 1 vector that consists of the 4 entries of each respective row in the camera projection matrix. The first plane that we are going to look at is the principal plane, and we'll see that the principal plane is actually given by the third row of the camera projection matrix. We have seen earlier on that the definition of principal plane is a plane that lies on the xy plane of the camera coordinate frame, as well as it must contain the camera center. And Since it contains the camera center, what this means is that any point that lies on the principal plane, it must be projected onto a line at infinity that is given by the equation over here, x, y, and 0. The third coordinate here has to be 0 because this has to be an ideal point in order for it to lie at the line at infinity. So looking at this particular equation over here, px equals to x, y, and 0. If we were to rewrite P, the projection matrix, in terms of each row of the matrix, you can see that it's P1 transpose, P2 transpose, and P3 transpose multiplied by X. And this must be equal to X, Y, and 0, since it must be projected into the line at infinity. What we can see here is that since the third element of the projection must be at 0, it simply means that the last entry over here, which is the last row of the projection matrix multiplied by x, it must be equals to 0, which gives rise to this equation over here, P3 transpose x must be equals to 0. And since we have defined earlier on that x to be a set of point or to be any point that is lying on the principal plane, what this means is that this relation here defines the incidence relation, and this says that x, which lies on the principal plane, must also lie on this plane that is being defined by P3 transpose, and hence this P3 transpose must be the same as the principal plane. So the other set of planes, the other two planes that can be defined by the remaining rows of P1 and P2 are the axis planes. And we'll see that these planes, for example, P1 is defined to be the plane that contains the camera center, which is denoted by C over here, as well as the line in the image coordinate frame where x equals to 0. And this essentially means that this is the y axis, which is given by this guy. So this means that P1 has to be this particular plane that contains this line where x equals to 0, as well as the camera center that is denoted by this point over here. Similarly, P2 is defined by the camera center as well as the line where y equals to 0, and this is essentially equals to the x-axis of the image coordinate frame. We can see that this is the line and the camera center is here, so P2 is essentially defined by this plane that contains the x-axis as well as the camera center. And we can see that this relation is true. Let's first consider a set of points, any points that lies on P2. So this point, let's denote it by x. According to our definition, this point is defined to lie on the plane P2. That means that the incidence relation P2 transpose multiplied by the dot product of P2 transpose and x, it must be equals to 0 for x to be lying on P2. And hence we can see that if we were to project these points x that lies on P2, any points that lies on P2, it must all be projected onto this line, which is the x-axis at y equals to 0 as seen earlier on. And this is true because we can see that the dot product of P2 transpose, which is the second row of P, we can see that, let's say if we write this relation into this P1 transpose, P2 transpose, and P3 transpose multiplied by x over here. So the second row multiplied by this guy over here, it must always be equals to 0, which is given by the incidence relation, since we define this set of points to be lying on the plane. And the first element of this can be any point, which is x, and the last one, P3 transpose, the last row of the projection matrix multiplied by x, can be also anything which is denoted by w. So what this simply means is that any point that lies on P2 will be projected to the x-axis, since any point here, the y element of this projection is going to be 0. So now we have proven that P2 must contain this line where y equals to 0, which is essentially the x-axis. The next step to the proof is that we must also prove that this plane P2 contains the camera center. This is easy because from the null space equation that we have seen earlier on, that P, the projection of a camera center, it must be equals to 0, equals to undefined point of 1000 transpose over here. And so it also follows that P2 transpose, since P multiplied by C, this means that P1 transpose, P2 transpose, and P3 transpose multiplied by C, it must be equals to 000. And what this means is that the second row multiplied by C, P2 transpose multiplied by C, must also be 0. Hence, this shows the incidence relation of C with the plane P given by the second row of the projection matrix over here. Hence, this means that the camera center, it must also lie on the plane P2, as well as that the line here, which is the x-axis, it must also lie on the plane P2. This proves our definition over here that P2, which is the second row of the camera projection matrix, it is the axis plane that contains the line of x-axis as well as the camera center. Now, the last thing that we can get from a camera projection matrix is the principal point. So since we have defined and this principal point is what we have defined earlier on, is defined to be the point that intersects the principal axis, the point of intersection of the principal axis and the image plane. So this is the principal point over here. And we have seen earlier on that P3, the third row of the camera projection matrix, P1 transpose, P2 transpose, and P3 transpose. So the third row over here gives us the principal plane. What this means is that the first three elements of this principal plane essentially gives us the direction of the normal vector of this principal plane. So this is our principal plane over here, which is given by P3 transpose. And that means the direction of the principal axis, which is perpendicular to the principal plane, is essentially given by the first three elements of the third row of the camera matrix. And we can also treat this direction over here as an ideal point that is given by the direction of the principal axis of our camera coordinate frame. This ideal point over here in the direction of the principal axis given by P hat 3 over here. This point here, it actually projects onto the image at the principal point. This can be mathematically given by this projection over here, where this is the P3 hat here, represents the ideal point, and it's projected by the projection matrix onto x0, which represents the principal point. And we can rewrite this relation as capital M multiplied by M3, where the capital M here represents the first 3 by 3 entries of the camera projection matrix, and M3 here represents the third row of this M matrix, of this 3 by 3 M matrix, which is rewritten as M1 transpose, M2 transpose, and M3 transpose over here. So earlier on in the camera projection matrix that we have defined from the basic pinhole camera model, we have seen that any points, mathematically, any points in the 3D space can be mapped via this projection matrix onto the image. But in reality, only half of these points in the 3D space, in particular those that are lying in front of the camera, can be observed on the image. We can define this half of the points in space using the principal axis vector. And the principal axis vector is actually given by V equals to the determinant of M, which is the first 3 by 3 entries of the P matrix over here, P4, which is the first 3 by 3 entry of the camera projection matrix, and multiply by the last row of the M matrix, which is given by this, which is rewritten by as this guy. We have seen that M3 here defines the direction of the principal axis, because we have seen that P is given by rewrite into P1 transpose, P2 transpose, and P3 transpose. And this guy here, the last row, it represents the principal plane. And we have said earlier on that the first three entries of principal plane denotes the direction vector. The first three elements of this, which we earlier on defined as P hat 3 transpose. And now we can see that these first three elements of this, if we were to rewrite the projection matrix into M and P4, the first three elements of the last row is actually given by the last row of the M matrix, which we denote by M3 transpose over here, which means that M3 transpose is actually the principal axis that we have seen earlier on. However, we must also note that this particular vector M3 transpose over here is only defined up to a certain sign. With respect to a world frame, we do not know whether this is pointing this direction or pointing the other direction. So, but this ambiguity can be resolved using sign of the principal axis that is obtained from the determinant of M. The determinant of M is essentially equivalent to the sign area distance. So if we were to write M as M1 transpose, M2 transpose, and M3 transpose, we can treat the first row as I, J, and K, and the second and third row as this. So what it means when we write the determinant, when we are computing the determinant of this guy over here, it is equivalent to the cross product of the two rows. Geometrically, what it means here is that I have two vectors on the principal plane. I'm going to I'm going to do a cross product of these two, and this is going to give me another vector that tells me the sign distance of this. It's either going to be pointing this direction depending on the sign of these two vectors. If this vector is pointing the other way, this means that I would end up to have another vector. Determinant of this is going to be negative in the other direction over here. So by doing this, I'll be able to figure out that this principal axis is actually pointing to, and figure out the set of points that is lying in front of the camera. So a summary of the properties that we can obtain from the camera projection matrix is given by this table over here. We have seen that the camera center is essentially given by the right now of this equation over here, since we know that the projection of the camera center has to be projected onto a point of 0, 0, 0, an undefined point of 0, 0, 0. We will see that this null space is essentially given by the inverse of the M matrix, where M is the first 3 by 3 matrix of the projection. Since this is a finite camera, but we'll see that this invertible 3 by 3 matrix that can be used to find out the null space. We can actually verify this. If we take M multiplied by and P multiplied by this guy over here, P4 1. This essentially gives us P4 minus P4 plus P4, which has to be a zero vector, and this is equivalent to this equation over here, which satisfies this equation over here. And then towards the end of the lecture, we'll also look at the camera at infinity, where the first 3 by 3 element of the camera projection matrix is no longer invertible, and the camera center lies at infinity, where it has to be given by this equation over here. We'll look at this in more detail in a moment. So we also look at the columns of the camera matrix. The first three columns define the three vanishing points that corresponds to the directions of the axis of the world frame, and the fourth column corresponds to the projection of the origin of the world frame onto the image. And then we've also seen the third row of the camera matrix represents the principal plane, and there are also two additional axis planes that contains the camera center as well as the x-axis or the y-axis of the image coordinate frame that is defined by the first row and the second row of the camera projection matrix. And we also look at the principal point. So essentially, this is the projection of the ideal point that is given by the normal vector from the principal plane, which is the first three entries of the third row of the principal plane. Then finally, we look at the principal ray, and this ray, this principal axis, it actually defines the direction of the camera principal axis. By defining this direction, we'll also be able to figure out the half set of points that is lying in front of the camera that can be projected onto an image for observation.